Picture this. The universe whispers its secrets through invisible light, beams of energy so powerful they could pierce through planets. Gamma rays, the universe's brightest flashlights, have always followed the rules until now. Something strange is happening in the depths of space. These cosmic powerhouses aren't behaving the way they should, breaking every astrophysics textbook in sight. Scientists are calling it the InfraredTeV Crisis, and it's turning everything we thought we knew about gamma rays upside down. Today, we're diving into this cosmic detective story, where the universe is the crime scene and gamma rays are leaving behind clues that don't make sense. Why are these energetic particles suddenly going rogue? What hidden forces are messing with the rules of deep space? Stick around, because by the end of this video, you'll see the night sky in a whole new light and understand why this mystery could rewrite the laws of physics as we know them. Let's peel back the layers of this cosmic mystery by starting with the basics. Gamma rays are not your ordinary light. They are the most energetic form of electromagnetic radiation in the universe, packing enough punch to outshine a supernova. Imagine light on steroids, waves of energy so intense they can travel billions of light years across space, carrying secrets from the most violent events in existence. But where do they come from? Gamma rays are born in the chaos of extreme cosmic phenomena. Think collapsing stars, colliding neutron stars, or the superheated edges of black holes. These are the universe's particle accelerators, ripping atoms apart and flinging gamma rays into the void like cosmic fireworks. Now, let's talk about what makes gamma rays so special. Unlike visible light, which our eyes can see, gamma rays operate on a completely different level. Their wavelengths are unimaginably short, smaller than the nucleus of an atom, and their frequencies are sky-high. This gives them unique properties. They can penetrate almost anything from interstellar dust clouds to the densest materials on Earth. That's why they're so hard to detect. Catching a gamma ray is like trying to grab a bullet with your bare hands. Scientists use specialized telescopes like the Fermi Gamma Ray Space Telescope, which orbits above Earth's atmosphere to avoid interference. These detectors don't work like your backyard telescope. Instead, they track the secondary particles created when gamma rays collide with atoms in the upper atmosphere, turning an invisible signal into something we can measure. But why should we care about these elusive rays? Gamma rays are cosmic messengers. They tell us stories about the universe's most extreme environments, places where matter is twisted, temperatures soar to billions of degrees, and gravity bends space itself. For instance, when two neutron stars merge, the resulting gamma-ray burst can outshine an entire galaxy for a few seconds. These bursts are like cosmic breadcrumbs, leading us to events that shape the universe. They also help us probe the invisible structures of space, like the magnetic fields threading between galaxies or the elusive nature of dark matter. Without gamma rays, we'd be missing a crucial chapter in the story of the cosmos. Here's something fascinating. Gamma rays don't just come from distant cataclysms. Even lightning on Earth produces them, albeit in much smaller doses. These terrestrial gamma-ray flashes were discovered by accident in the 1990s, proving that high-energy physics isn't just a distant space phenomenon. It's happening right over our heads, yet despite their power, gamma rays are surprisingly delicate. Traveling across the universe, they can be absorbed or scattered by interstellar gas, or even transformed into other particles if they collide with infrared light, which brings us back to the InfraredTeV Crisis. Why? Because this delicate dance of energy is at the heart of why gamma rays are suddenly breaking the rules. But that's a story for the next part of our cosmic detective tale. For now, remember this: gamma rays are more than just energy. They're the universe's way of shouting its most explosive secrets across the void, and we're just starting to listen. Now, let's step into the realm of predictability, because even in the chaotic universe, gamma rays were supposed to follow certain rules. According to our best scientific models, these high-energy photons should behave in ways we can calculate and anticipate. Think of it like a cosmic game of billiards. When a gamma ray is born in the heart of a collapsing star or a black hole's jet, its journey through space isn't random. It's governed by the laws of physics we've spent centuries unraveling. First, let's talk about absorption. Gamma rays are incredibly powerful, but they're not invincible. When they travel through space, they can be absorbed by interstellar gas and dust, especially if they encounter dense regions like nebulae. The thicker the material, the more likely the gamma ray will be stopped in its tracks. Scientists use this behavior to map out the invisible structures of the universe. By measuring how gamma rays dim as they pass through certain areas, we can estimate the density of cosmic matter in their path. Then there's scattering. Even if a gamma ray isn't fully absorbed, it can bounce off particles in space, changing direction like a pinball. This is where the Compton effect comes into play, a phenomenon where gamma rays lose energy as they collide with electrons. The result, the gamma ray's wavelength gets longer, shifting it down the electromagnetic spectrum. Over great distances, this means some of the most energetic gamma rays might degrade into X-rays or even lower energy photons by the time they reach us. But here's where things get especially interesting: pair production. When a gamma ray with enough energy, usually above 1 million electron volts, meets a nucleus or even another photon, it can spontaneously transform into matter. That's right, energy literally becomes particles, typically an electron and its antimatter counterpart, a positron. This mind-bending process, predicted by Einstein's famous equation, is one of the key ways gamma rays are expected to lose energy in space. Now let's zoom out to the big picture. Astrophysicists have built sophisticated simulations to predict how gamma rays should move through the cosmos. These models account for all the interactions I just mentioned: absorption, scattering, pair production, plus the influence of magnetic fields and background radiation. The consensus was clear: gamma rays from distant sources should arrive at Earth with a predictable spectrum. Their energies spread in a particular pattern based on how far they've traveled and what they've encountered. Take blazars, for example. These supermassive black holes shoot jets of gamma rays directly toward us, acting like cosmic lighthouses. According to theory, the gamma rays from these jets should show a steady drop-off at the highest energies, thanks to interactions with infrared light filling the universe. This drop-off is called the gamma-ray horizon, and it's a cornerstone of our understanding. But here's the catch: nature doesn't always follow the script. Observations from telescopes like Fermi and HESS have thrown a wrench into these clean predictions, revealing gamma rays that are either too energetic or too numerous given their distance. It's as if some of them are slipping through cosmic obstacles unscathed, breaking the rules we thought were set in stone. That's the heart of the InfraredTeV crisis, and it's forcing scientists to ask: are our models missing something fundamental, or is the universe playing by a new set of physics we haven't discovered yet? For decades, these models worked beautifully, explaining everything from gamma-ray bursts to the diffuse glow of the cosmic background. But now, with the InfraredTeV crisis shaking the foundations, the scientific community is in a race to rewrite the playbook or uncover the hidden forces bending the rules. Now picture this: a universe that suddenly stops playing by the rules. That's exactly what scientists faced when they first stumbled upon the InfraredTeV crisis. It all started with a series of baffling observations that didn't fit the cosmic playbook. Telescopes like Fermi and HESS, designed to catch the faintest whispers of gamma rays from across the universe, began picking up signals that made no sense. Gamma rays arriving from distant galaxies were packing way more energy than our models predicted. It was as if these photons had somehow cheated the system, dodging the obstacles that should have sapped their strength over billions of light years. The first major clue came from blazars, those brilliant beacons powered by supermassive black holes. According to theory, their gamma rays should hit a wall, the gamma-ray horizon, where interactions with the universe's infrared background light would drain their highest energies. But the data told a different story. Gamma rays with tera-electronvolt energies, which should have been absorbed long before reaching us, were flooding detectors. Imagine throwing a ball into a thick fog, expecting it to slow down, only to watch it rocket through untouched. That's the level of confusion this sparked. Even more puzzling were the numbers. The expected drop-off in high-energy gamma rays. It wasn't just slightly off, it was missing entirely in some cases. Telescopes like MAGIC and Veritas doubled down on these observations, confirming that something was fundamentally wrong with our understanding. Either the infrared background light, which fills the space between galaxies, was far weaker than we thought, or some unknown process was shielding these gamma rays from its effects. Both possibilities upended decades of astrophysics. Then came the real head-scratcher, the timing. Some gamma-ray bursts flared with energies that defied not just distance but also time. In one famous case, a burst from a galaxy over 4 billion light-years away sent photons with energies so high they should have been stripped down by pair production long before Earth. Yet there they were, hitting our telescopes with undimmed fury. It was like receiving a letter sealed centuries ago, only to find the ink still wet. What makes this crisis so explosive isn't just the anomalies themselves, it's what they imply. Our models of gamma-ray propagation aren't just incomplete, they might be missing entire chapters of physics. Could dark matter be intercepting these rays in ways we can't yet see? Are there invisible quantum fields bending the rules, or is the universe's infrared background, which we've used as a cosmic measuring stick, far patchier than we imagine? Each question cracks open new uncertainties. The InfraredTeV Crisis isn't just a scientific hiccup, it's a revolt against the status quo. For the first time, we're staring at gamma rays that refuse to follow the paths we've meticulously charted. And that's exhilarating, because every time the universe throws us a curveball, we're forced to dig deeper, think bigger, and rewrite the textbooks. Right now, somewhere out there, a gamma ray is breaking the rules. And its defiance might just lead us to the next great cosmic revelation. Now, let's rewind the cosmic clock. The InfraredTeV Crisis might feel like a sudden shock, but gamma rays have been throwing us curveballs for decades. History tells us that every time we think we've got these high-energy photons figured out, they surprise us all over again. One of the first major wake-up calls came in the 1960s with the discovery of gamma-ray bursts. These sudden, intense flashes of gamma rays, some lasting mere milliseconds, left scientists completely baffled. At first, nobody could even agree on where they were coming from. Were they originating in our own Milky Way or from distant galaxies? It took years of debate and better telescopes to confirm that these bursts were coming from billions of light-years away, meaning they were releasing unimaginable amounts of energy. The fact that we could detect them at all defied early expectations. Then there was the mystery of the gamma-ray background. In the 1970s, satellites designed to monitor nuclear tests stumbled upon something unexpected, a faint, persistent glow of gamma rays coming from all directions. This wasn't from any single source but seemed to fill the entire sky. At first, scientists assumed it was just noise, maybe leftover radiation from cosmic rays interacting with interstellar gas. But as observations improved, it became clear this background was real, and nobody could fully explain it. Some of it came from known sources like pulsars and supernova, but a significant portion remained unaccounted for. Decades later, we're still piecing together where all that diffuse gamma radiation is coming from. Perhaps the most famous historical anomaly was the Great Annihilator near the center of our galaxy. In the early 1990s, telescopes detected an intense source of gamma rays coming from the region around Sagittarius, a star, the supermassive black hole at the Milky Way's heart. The energy signature suggested something was producing vast amounts of positrons, antimatter counterparts to electrons, which then annihilated with normal matter, releasing gamma rays. The problem, nobody could figure out what was generating all those positrons. Dark matter, a hidden pulsar. Even today, the exact mechanism remains a topic of fierce debate. What makes these past puzzles so relevant to the InfraredTeV crisis is that they all had one thing in common. They forced scientists to rethink fundamental assumptions. Each time gamma rays acted out of line, it wasn't just a quirk. It was a signal that our understanding of the universe was missing something big. And just like those earlier mysteries, the InfraredTeV crisis isn't just about a few odd data points. It's pointing to gaps in our knowledge that could reshape entire fields of physics. The difference this time, scale. Earlier anomalies were localized, strange bursts here, unexplained background radiation there. The InfraredTeV crisis, though, is systemic. It's not just one source or one type of observation acting up. Across multiple galaxies and energy ranges, gamma rays are behaving in ways that shouldn't be possible. That's why this isn't just another puzzle, it's a full-blown revolution in how we see the universe's most energetic light. Looking back at these historical surprises reminds us of something crucial. Every time gamma rays break the rules, science leaps forward. The mysteries of yesterday became the breakthroughs of today, and if history is any guide, the InfraredTeV crisis won't just be solved, it'll unlock entirely new chapters in our cosmic story. So while the anomalies might seem frustrating now, they're also our greatest opportunity, because when the universe refuses to follow the script, that's when we learn the most. Now let's zoom in on the energy ranges at the heart of this mystery. The InfraredTeV crisis gets its name from two critical bands of energy, infrared and tera-electronvolt, or TV. These might sound like technical terms, but they're the keys to unlocking why gamma rays are misbehaving. First, consider infrared light. We often think of it as the warmth we feel from the sun or the glow of a heat lamp, but in space it's a cosmic fingerprint. Dust clouds, young stars, and even distant galaxies emit infrared radiation, and it plays a surprising role in gamma-ray journeys. When high-energy gamma rays travel through the universe, they don't always make it to our telescopes unscathed. They can collide with infrared photons, the particles of infrared light, and these collisions cause the gamma rays to lose energy or even vanish entirely. This interaction is called pair production. Here's how it works. When a gamma ray smashes into an infrared photon, they can transform into a pair of particles, an electron and its antimatter twin, the positron. This process effectively erases the gamma ray from our observations. Scientists have long factored this into their models, expecting certain gamma rays to fade out over vast distances. But here's the twist. In the InfraredTeV crisis, we're seeing gamma rays that shouldn't have survived these collisions, yet they're reaching us anyway. It's like spotting a marathon runner who somehow didn't get tired, even after running through a field of obstacles. Now shift to the other half of the puzzle, tera-electronvolt energies. TV gamma rays are the heavyweights of the cosmic light spectrum, packing trillions of times more energy than visible light. These extreme photons usually come from the universe's most violent events, supernova remnants, colliding stars, or the jets of supermassive black holes. But their behavior is just as puzzling. When TV gamma rays travel through space, they should interact with the cosmic infrared background, the faint glow of infrared light left over from all the stars and galaxies in the universe. These interactions should, in theory, dim or block TV gamma rays over long distances. Yet, telescopes like HESS and MAGIC have detected TV gamma rays from galaxies billions of light-years away. According to our models, these photons should have been absorbed long before they reached us. It's as if someone turned off the obstacles mid-race, letting the runner sprint unchallenged. This mismatch between prediction and observation is the core of the InfraredTeV crisis. Why does this matter? Because these energy bands aren't just arbitrary lines on a spectrum. They're windows into the universe's hidden rules. If gamma rays can slip past barriers they shouldn't, it suggests there's something fundamentally wrong with our understanding of how light and matter interact across cosmic distances. Maybe the infrared background is fainter than we thought. Maybe there's an unknown process shielding gamma rays, or perhaps our theories about the universe's structure need a rewrite. What makes this especially intriguing is that infrared and TV energies aren't just passive players, they're active shapers of cosmic history. Infrared light traces the universe's dusty nurseries where stars are born, while TV gamma rays mark the aftermath of its most cataclysmic deaths. If we can't trust how these energies interact, our entire timeline of cosmic events from galaxy formation to black hole growth might need re-evaluation. This isn't just about fixing a glitch in the data. It's about confronting the possibility that the universe has been hiding a few cards up its sleeve. And as we'll see next, the telescopes and detectors trained on this crisis are revealing even more layers to the mystery. Now, let's turn our attention to the hard evidence that first brought the InfraredTeV crisis into sharp focus. The mystery didn't emerge from pure theory. It was the telescopes, those silent watchers of the cosmos, that handed scientists this puzzle wrapped in gamma rays and infrared light. One of the first major clues came from the Fermi-Large Area Telescope, or Fermi-LAT for short. Orbiting Earth since 2008, this telescope has been mapping the sky in gamma rays with unprecedented precision. Fermi-LAT expected to see a predictable drop-off in gamma rays from distant galaxies, thanks to those interactions with infrared light we discussed earlier. Instead, it spotted gamma rays arriving from galaxies so far away that, by all known physics, they should have been absorbed long before reaching us. Imagine mailing a letter with no address, only for it to show up at the right doorstep against all odds. That's the level of bafflement Fermi-LAT delivered. Then there's HESS, an array of telescopes nestled in the Namibian desert, specializing in catching the highest energy gamma rays, the TV photons. HESS didn't just find a few of these rebellious gamma rays, it found them in abundance, streaming from active galaxies billions of light years away. According to every existing model, the universe's infrared background should have acted like a thick fog blocking these photons, yet HESS saw them shining through clear as day. It's as if the fog simply parted for them. MAGIC, another ground-based observatory perched in the Canary Islands, doubled down on these findings. With its massive mirrors, MAGIC detects gamma rays by the faint flashes of blue light they create when hitting Earth's atmosphere. When it turned its gaze to distant blazars galaxies with supermassive black holes spewing jets of gamma rays straight at us, it saw TV photons that should have been annihilated by the infrared background. But there they were, defying expectations. What makes these observations so compelling is their consistency. Different telescopes, different technologies, even different methods of detection, yet all pointing to the same discrepancy. It's not a glitch in one instrument or a fluke in the data. The universe is genuinely sending us gamma rays that, by our current understanding, shouldn't exist at these distances. But here's where it gets even more intriguing. Some of these gamma rays arrive with companions. Fermi-LAT has detected cases where lower energy gamma rays make the trip unscathed, while their higher energy counterparts, the ones that should be more easily absorbed, also arrive intact. It's like watching two runners tackle the same obstacle course, one lightly dressed and the other carrying a heavy backpack, yet both finish at the same time. This mismatch throws another wrench into the works, suggesting that our assumptions about how gamma rays lose energy might be missing a crucial piece. The sheer scale of these observations adds weight to the crisis. We're not talking about a handful of anomalies buried in noisy data. These are robust, repeatable detections across multiple sources and distances. When HESS and MAGIC peer into the depths of space, they're not just seeing one or two defiant gamma rays, they're seeing a pattern. a trend that refuses to fit into our cosmic playbook. And it's not just about what these telescopes see, it's also about what they don't see. Models predict that certain gamma-ray sources should appear dimmer or even invisible at specific distances due to absorption. Yet time and again, these sources shine brighter and clearer than they have any right to. It's as if the universe forgot to enforce its own rules. This isn't just a challenge for astrophysicists, it's a golden opportunity. Every anomaly, every unexpected detection is a clue pointing towards something new. Maybe the infrared background is patchier than we thought. Maybe gamma rays have a sneaky way to bypass absorption. Or perhaps there's an entirely unknown process at work, something that rewrites the rules of light's journey through the cosmos. What's certain is that the telescopes have spoken, and their message is clear. Our understanding of gamma rays is incomplete. The next step, digging deeper into how these observations clash with theory, and that's where things get even more fascinating. Now, let's peel back the layers of this cosmic mystery and see why these observations have left scientists scratching their heads. The InfraredTeV Crisis doesn't just challenge a single idea, it shakes the foundations of how we think gamma rays interact with the universe. Take black holes, for example. These cosmic giants are among the most powerful gamma-ray factories in the universe. When matter spirals into a supermassive black hole at the heart of a galaxy, it heats up and emits jets of radiation, including gamma rays. Our models predict how these jets should behave, how their light should dim as it travels through the infrared background. But the data from Fermi-LAT, HESS, and MAGIC show something entirely different. The gamma rays aren't fading as they should. It's like expecting a flashlight beam to grow dimmer with distance, only to find it stays just as bright no matter how far you go. This mismatch forces us to ask, are we missing something fundamental about how black holes energize these rays? Or is there some hidden process that's shielding gamma rays from absorption? Then there are supernova, the explosive deaths of massive stars. These events are another key source of gamma rays, especially at lower energies. Current theories suggest that gamma rays from supernova remnants should interact strongly with the infrared background, particularly over vast intergalactic distances. Yet observations reveal that these gamma rays, too, are arriving in numbers that defy expectations. If our models of supernova physics are correct, these rays should be getting absorbed way before they reach us. The fact that they aren't suggests there's a gap in our understanding, either about how supernova produce gamma rays or how those rays travel through space. Dark matter adds another layer of intrigue. Some scientists have proposed that dark matter particles, which make up most of the universe's mass but remain invisible to our telescopes, could be influencing these gamma ray anomalies. One idea is that dark matter might decay or collide, producing gamma rays that could explain some of the unexpected signals. But here's the catch: if dark matter is the culprit, its behavior would have to be far more complex than our current theories allow. It would need to produce gamma rays in just the right way to mimic the observed patterns without contradicting other well-tested predictions about dark matter. So far, no model has fully bridged that gap. What's striking is how widespread the contradictions are. It's not just one type of gamma ray source or one specific energy range that's behaving oddly. It's multiple sources across the spectrum. This suggests the problem isn't with any single astrophysical object, but with our broader understanding of how gamma rays propagate. Maybe the infrared background isn't as uniform as we assume. Perhaps there are regions of space where the fog of infrared light is thinner, allowing gamma rays to slip through. Or maybe there's an entirely new kind of interaction between gamma rays and other particles that we haven't yet discovered. The crisis also exposes how interconnected our models are. A flaw in our understanding of gamma ray absorption doesn't just affect gamma ray astronomy, it ripples out to other fields. For instance, if we're wrong about how gamma rays lose energy, it could throw off estimates of how far away certain galaxies are or how energetic their black holes truly are. This isn't just a theoretical puzzle, it's a practical problem with real consequences for how we map and study the universe. So where does this leave us? For now, the InfraredTeV Crisis stands as a humbling reminder that the universe still holds surprises. Every time we think we've got the rules figured out, nature throws us a curveball. But that's the thrill of science. It's in these gaps, these contradictions, that the next big breakthroughs are waiting. The question isn't just why gamma rays aren't behaving as expected. It's what new physics, what unseen phenomena are out there rewriting the rules. Now, let's turn our attention to one of the most intriguing possibilities lurking in the shadows of this cosmic puzzle: dark matter. You've probably heard of dark matter before, that mysterious, invisible substance making up roughly 27% of the universe. It doesn't emit, absorb, or reflect light, which makes it incredibly hard to detect. Yet, its gravitational pull shapes galaxies and bends the fabric of space itself. But here's where things get even more fascinating. Some scientists believe dark matter might hold the key to the InfraredTeV Crisis. Imagine dark matter particles as cosmic ghosts silently drifting through space. Occasionally, these particles could collide or decay, annihilating each other in bursts of energy. When that happens, they might produce gamma rays, the very same gamma rays we're detecting in unexpected ways. If this is true, it would mean that some of the anomalous signals we're seeing aren't just coming from black holes or supernova, but from the hidden dark matter scaffolding of the universe. The evidence for this idea comes from a few tantalizing clues. First, there's the distribution of gamma ray emissions. In regions where we'd expect dark matter to be densely concentrated, like the centers of galaxies or galaxy clusters, we sometimes see excess gamma rays that don't match known astrophysical sources. The Fermi-LAT telescope, for example, has picked up unexplained gamma ray glows from the Milky Way's core, a place teeming with dark matter. These signals align with what some dark matter models predict: particles crashing together and releasing energy. Then there's the energy spectrum of these gamma rays. Dark matter annihilation or decay would produce gamma rays at very specific energies, depending on the mass of the particles involved. Some of the observed gamma ray excesses line up eerily well with these predicted energy bumps. It's like finding a fingerprint at a crime scene, one that just happens to match a suspect we've been searching for decades. But before we declare the case closed, let's talk about the hurdles. For starters, dark matter interactions would need to be finely tuned to explain the InfraredTeV Crisis. If dark matter is producing gamma rays, it can't be making too many or too few just enough to account for the anomalies without contradicting other observations. That's a tricky balance to strike. Plus, alternative explanations like undiscovered pulsars or other energetic cosmic objects could also be responsible for the excess gamma rays. Without a smoking gun, it's hard to rule these out. Another challenge is that dark matter models still can't fully explain why gamma rays aren't being absorbed as expected. Even if dark matter is producing extra gamma rays, why would they behave so differently when traveling through the infrared background? It's possible that dark matter interactions could somehow alter the way gamma rays propagate, but this would require new physics beyond our current theories. Despite these uncertainties, the dark matter hypothesis remains a compelling avenue of research. Experiments are underway to test it further, from underground detectors hunting for dark matter particles to telescopes scanning the skies for more gamma ray anomalies. If dark matter is behind the InfraredTeV Crisis, it wouldn't just solve a cosmic mystery, it would open a new window into understanding the invisible majority of our universe. Of course, science thrives on skepticism, and this idea is no exception. Some researchers argue that the evidence for dark matter's involvement is still too circumstantial. Others point out that modifying existing astrophysical models might be a simpler solution than invoking exotic particles. But that's the beauty of the scientific process. Every hypothesis gets put through the ringer until only the strongest survive. So where does this leave us? Dark matter offers a tantalizing possibility, but it's not the only game in town. The search for answers continues, with astronomers and physicists poring over data, refining models and debating possibilities. One thing's for sure: whether the culprit turns out to be dark matter or something else entirely, solving the InfraredTeV crisis will rewrite our understanding of the cosmos. And that's a discovery worth waiting for. Of course, dark matter isn't the only player in this cosmic whodunit. Let's shift gears and explore some other intriguing possibilities that could explain the InfraredTeV crisis, because in science it's always wise to keep an open mind. One compelling angle is the idea of unknown astrophysical processes. Think about it: the universe is full of extreme environments we're still barely beginning to understand. Take blazars, for instance. These supermassive black holes at the centers of galaxies shoot out jets of particles at nearly the speed of light, generating gamma rays in ways that can sometimes defy expectations. Could there be something unusual happening in these jets, some unaccounted for physics that's skewing our observations? Some researchers suggest that turbulent magnetic fields within these jets might accelerate particles differently than our models predict, leading to gamma ray emissions that don't quite line up with theory. Then there's the question of cosmic rays, high-energy particles racing through space. When these collide with interstellar gas, they can produce gamma rays. But what if there's more to this process than we've assumed? Maybe the interactions between cosmic rays and certain types of gas or dust are more complex than our current equations allow. For example, if cosmic rays are hitting dense pockets of cold molecular gas in unexpected ways, they might generate gamma rays with energies that puzzle us. It's like trying to predict the path of a ricocheting bullet in a room you've never seen. Sometimes the chaos throws you a curveball. Now, let's talk about something more mundane but equally important: instrumental errors. Even the best telescopes and detectors aren't flawless. Could calibration issues or data processing glitches be muddying the waters? Fermi-LAT and other instruments rely on sophisticated algorithms to filter out noise and pinpoint gamma-ray signals. If there's a subtle bug in the code, or if we're misinterpreting the data, it could create the illusion of anomalies where none exist. Scientists constantly cross-check their findings to rule this out, but it's always a factor worth considering. After all, when you're dealing with the faintest whispers of light from across the universe, even a tiny misstep can lead to big confusion. But what if the answer lies in something far more radical: new physics beyond the standard model? This is where things get really exciting. The standard model has been a triumph of modern science, but it's incomplete. It doesn't account for gravity, dark matter, or dark energy. Could the InfraredTeV crisis be a hint of deeper laws waiting to be discovered? One wild but tantalizing idea involves quantum gravity. At the smallest scales, space-time might be frothy and chaotic, like the surface of a boiling pot. If gamma rays interact with this quantum foam as they travel, it could subtly alter their behavior, making them appear to defy our expectations. Another fringe theory suggests that photons, the particles of light, might not all behave the same way. Some could have tiny differences in how they interact with the fabric of the universe, leading to puzzling patterns in gamma-ray observations. It's a long shot, but in science, even the craziest ideas deserve a hearing until the evidence rules them out. Here's the bottom line: while dark matter is a leading suspect in the InfraredTeV crisis, it's far from the only one. Whether it's undiscovered astrophysical phenomena, quirks in our instruments, or glimpses of physics beyond our current understanding, each possibility opens new doors to exploring the universe. The next breakthrough might come from a telescope spotting an unexpected gamma-ray flare, a physicist tweaking an equation, or even a graduate student noticing a weird pattern in old data. And that's the thrill of it all. Every mystery in astrophysics is a chance to learn something extraordinary, not just about gamma rays, but about the very laws that govern reality itself. So as we wait for more clues, one thing's certain, the universe still has plenty of surprises up its sleeve. Now here's where things get even more puzzling. The Fermi Large Area Telescope, one of our most powerful tools for studying gamma rays, has thrown a wrench into the works with some head-scratching observations. Picture this: you've got a telescope designed to map the high-energy universe with precision, and instead of confirming what we thought we knew, it's serving up data that just doesn't add up. That's the Fermi-LAT paradox in a nutshell, a series of contradictions that have left scientists scratching their heads and digging deeper for answers. Let's break it down. Fermi-LAT has been scanning the skies for over a decade, cataloging gamma-ray sources like pulsars, supernova remnants, and of course, those enigmatic blazars. But here's the kicker: some of the gamma rays it's detected don't match the expected patterns. For instance, when astronomers look at distant blazars, they expect to see a certain drop-off in gamma-ray intensity at higher energies due to interactions with the cosmic microwave background, the afterglow of the Big Bang. But in several cases, Fermi-LAT has spotted gamma rays from these blazars that are too bright at those high energies, as if something's shielding them from the expected absorption. It's like seeing a flashlight beam through a thick fog bank when it should have been completely swallowed up. Then there's the mystery of the diffuse gamma-ray background. Fermi-LAT has mapped this faint glow of gamma rays coming from all directions, thought to arise from cosmic rays colliding with interstellar gas. But the distribution and intensity of this glow don't quite align with what our models predict. Some regions of the sky are brighter than they should be, while others are oddly dim. It's as if there's an invisible hand tweaking the gamma-ray output in ways we can't yet explain. One of the most confounding findings involves the Milky Way center. Fermi-LAT has detected an excess of gamma rays coming from this region, more than can be accounted for by known sources like pulsars or cosmic ray interactions. At first, researchers wondered if this could be the smoking gun for dark matter annihilations, since the center of our galaxy is thought to harbor a dense concentration of it. But here's the twist: the energy spectrum of these gamma rays doesn't perfectly match any of the leading dark matter models. It's close enough to be tantalizing, but just different enough to keep the debate alive. Could it be dark matter after all, or is there some other, more mundane explanation, like a population of undiscovered millisecond pulsars? And let's not forget the time variability issue. Fermi-LAT has caught gamma-ray flares from certain sources that rise and fall in brightness far faster than our theories say they should. For example, some blazars have shown gamma-ray outbursts that double in intensity over just a few minutes. Current models of particle acceleration in these jets struggle to explain how such rapid changes could occur. It's like watching a bonfire flicker from a candle's flame to a roaring blaze in seconds. Something about the physics here isn't playing by the rules. So why is all this so confounding? Because each of these discrepancies chips away at the foundations of our understanding. If gamma rays aren't behaving as predicted, it could mean there's something fundamentally missing from our models of particle physics, astrophysics, or both. Maybe we're underestimating the role of magnetic fields in shaping gamma-ray emission. Maybe there's an unknown population of cosmic accelerators lurking in the shadows. Or perhaps, as some daring theories suggest, we're seeing hints of physics beyond the standard model, a whisper of quantum gravity or even extra dimensions. The Fermi-LAT paradox isn't just a technical hiccup, it's a beacon pointing us toward gaps in our knowledge. And that's what makes it so exciting. Every contradiction is a clue, and every unexplained observation is an opportunity to rewrite the textbooks. As Fermi-LAT and future telescopes keep gathering data, one thing's clear: the universe isn't just stranger than we imagine, it's stranger than we can imagine. And that's the beauty of the hunt. Now let's turn our attention to another piece of this cosmic puzzle: cosmic rays. These high-energy particles, zipping through space at nearly the speed of light, might hold clues to why gamma rays aren't behaving as expected. Think of cosmic rays as the universe's own particle accelerators, crashing into gas, dust, and magnetic fields, and in the process sometimes creating gamma rays. But here's where it gets interesting. These interactions could be behind some of the anomalies we're seeing in the InfraredTeV Crisis. First, let's talk about where cosmic rays come from. Most are thought to originate from supernova, the explosive deaths of massive stars. When a star goes supernova, it blasts out shock waves that can accelerate protons and other atomic nuclei to extreme energies. These particles then travel across the galaxy, and when they collide with interstellar gas, they produce gamma rays through a process called pion decay. This is a well-understood mechanism, but what if something about these collisions isn't as straightforward as we thought? Take the diffuse gamma ray background we mentioned earlier. Fermi-LAT's map shows this glow isn't uniform, and one possible explanation lies in cosmic rays. If cosmic rays are interacting with patches of denser or more turbulent gas in unexpected ways, it could create those brighter or dimmer regions in the gamma ray sky. For example, in areas where magnetic fields are unusually strong, cosmic rays might be funneled or trapped, leading to more collisions and thus more gamma rays than our models predict. Conversely, in regions where cosmic rays are scattered or absorbed by yet-to-be-discovered structures, we might see fewer gamma rays than expected. Then there's the mystery of the Milky Way's gamma ray excess. Some researchers have proposed that cosmic rays, particularly those accelerated by undiscovered sources near the galactic center, could be responsible. Imagine a hidden population of supernova remnants or pulsars pumping out cosmic rays at a higher rate than we've accounted for. These particles could then collide with nearby gas, producing gamma rays in excess of what our current models anticipate. It's a tantalizing idea, but there's a catch. The energy spectrum of this excess doesn't perfectly match what we'd expect from standard cosmic ray interactions. This leaves room for more exotic explanations like dark matter, but it also suggests our understanding of cosmic ray physics might need tweaking. Another clue comes from blazars. These distant galaxies shoot out jets of particles, including cosmic rays, at nearly light speed. When these cosmic rays travel across intergalactic space, they can interact with photons from the cosmic microwave background, producing gamma rays. But here's the twist. Some blazars appear to emit gamma rays that survive this long journey with minimal absorption, as if they're getting a free pass. One possibility is that cosmic rays from these blazars are interacting with other particles or fields in ways we haven't accounted for, somehow shielding the gamma rays from being absorbed. Alternatively, perhaps the cosmic rays themselves are being re-accelerated along the way, giving the gamma rays an unexpected boost. And let's not forget the role of intergalactic magnetic fields. These invisible threads weaving through the cosmos can bend the paths of cosmic rays, potentially steering them into regions where they produce more gamma rays than we'd predict. If these fields are stronger or more tangled than we've assumed, they could be distorting the gamma ray signals we see, adding another layer of complexity to the InfraredTeV Crisis. So where does this leave us? Cosmic rays are clearly part of the story, but they're not the whole answer. Their interactions with matter, magnetic fields, and even dark matter could be muddying the gamma ray signals we observe, creating discrepancies that challenge our models. The key is figuring out which of these interactions are at play, and whether they're hiding new physics or just revealing gaps in our current understanding. What's exciting is that every anomaly, every unexpected gamma ray signature, is a breadcrumb leading us closer to solving this cosmic whodunit. Whether it's tweaking our models of cosmic ray acceleration or uncovering entirely new processes, the InfraredTeV Crisis is pushing astrophysics into uncharted territory. And that's where the real discoveries happen. Now, let's venture into another fascinating piece of the puzzle: intergalactic magnetic fields. These invisible forces stretch across the vast emptiness between galaxies, weaving a cosmic web that might hold the key to some of the gamma ray mysteries we've been grappling with. To understand their role, picture space not as a perfect vacuum, but as a dynamic arena filled with weak yet widespread magnetic fields. These fields are remnants of the universe's earliest moments, amplified over billions of years by the motion of charged particles and the collapse of large-scale structures. While they're incredibly faint, far weaker than Earth's magnetic field, their sheer scale means they can still play a major role in shaping how gamma rays travel. Here's how they might be stirring up trouble. When gamma rays zip through space, they can interact with lower energy light, like infrared or microwave photons, producing pairs of electrons and positrons. Normally, these particles would just fly off, but in the presence of intergalactic magnetic fields, their paths get bent. This deflection can cause the gamma rays to scatter or even appear to vanish from our detectors, creating gaps or distortions in the data. It's like trying to follow a flashlight beam through a foggy forest. Sometimes the light gets redirected in ways you don't expect. One striking example comes from observations of distant blazars. These cosmic lighthouses should pump out gamma rays in predictable patterns, but some of their signals arrive weaker or more spread out than models predict. One explanation: the gamma rays might be getting tangled up in the magnetic fields between galaxies. As those gamma rays convert into electron-positron pairs and back again, the fields could nudge them off course, smearing their arrival times or even splitting them into multiple faint signals. This would make blazars appear dimmer or more variable than they really are, adding yet another twist to the InfraredTeV Crisis. Then there's the mystery of the gamma-ray halo around our own Milky Way. Fermi-LAT has spotted a faint, bubble-like glow extending far beyond the galaxy's disk, and one leading theory points to cosmic rays interacting with these intergalactic fields. If magnetic fields beyond the Milky Way are trapping or redirecting high-energy particles, they could be creating this unexpected gamma-ray haze. It's a bit like discovering your backyard fence has been bending the wind in ways you never noticed. Suddenly, the weather patterns start making more sense. But here's the catch: measuring these fields is notoriously tricky. Unlike stars or gas clouds, they don't emit light or absorb it, so we have to rely on indirect clues. One method involves studying how they bend the paths of ultra-high-energy cosmic rays, particles so energetic they shouldn't exist under current physics. If these cosmic rays arrive from directions that don't match any known sources, it could mean intergalactic magnetic fields have been steering them, like invisible railroad tracks redirecting a speeding train. Another approach looks at the polarization of light from distant quasars, which can reveal how magnetic fields have twisted the light's journey across the cosmos. The implications are profound. If these fields are stronger or more tangled than we thought, they could be masking entire populations of gamma-ray sources or distorting our maps of the high-energy universe. Alternatively, they might be hiding entirely new physics, perhaps even signatures of dark matter or exotic particles. What's clear is that intergalactic magnetic fields are more than just cosmic scenery. They're active players in the InfraredTeV Crisis, reshaping gamma-ray signals in ways we're only beginning to decode. And as we peel back these layers, we're not just solving a puzzle, we're rewriting the rules of how the universe's most energetic light travels through the void. Next, we'll dive into another frontier of this mystery: quantum gravity, where the tiniest scales of physics might hold clues to the biggest cosmic surprises. Now, let's stretch our imaginations even further and explore one of the most thrilling and speculative ideas in modern physics: quantum gravity. This is where the rules of the very small could shake up our understanding of the very large, potentially offering clues to the InfraredTeV Crisis. Quantum gravity is the missing link in our map of the universe. We have two incredibly successful frameworks: quantum mechanics, which governs the behavior of particles at tiny scales, and general relativity, which describes gravity and the structure of spacetime. But these two don't play nicely together. Quantum gravity aims to bridge that gap, and some scientists think its effects might be imprinting themselves on gamma rays in ways we're only starting to glimpse. Here's the wild part. In some quantum gravity models, spacetime isn't the smooth, continuous fabric we usually imagine. Instead, it might be pixelated or grainy at the smallest scales, like a cosmic version of a digital photo zoomed in too far. If that's true, then ultra-high-energy gamma rays traveling across billions of light-years could interact with this granularity, subtly changing their properties along the way. One way this might show up is in the energy of gamma rays themselves. Normally, all gamma rays from the same source should travel at the same speed, the speed of light. But some quantum gravity theories predict that higher energy gamma rays could lag ever so slightly behind their lower energy counterparts because they're more sensitive to the bumps in spacetime. It's like rolling marbles over a sheet of sandpaper. The bigger marbles might jostle more, slowing them down just a fraction. If this is happening, it could explain why some gamma ray signals seem smeared out or arrive at slightly different times than expected. Then there's the idea of vacuum birefringence. Picture this: the quantum vacuum isn't truly empty but seething with particles popping in and out of existence. Some theories suggest that in the presence of strong magnetic fields like those near black holes or in intergalactic space, this quantum froth could act like a prism, splitting gamma rays based on their polarization. This could distort their signals in ways that mimic the anomalies we're seeing. Of course, these ideas are still on the fringes of physics. The effects would be incredibly subtle, and so far, no experiment has definitively spotted them. But here's why they're worth considering. If gamma rays are indeed being altered by quantum gravity, it wouldn't just solve the InfraredTeV crisis, it would revolutionize our understanding of reality. We'd have our first direct evidence that spacetime has a quantum structure, something theorists have been chasing for decades. That said, extraordinary claims require extraordinary evidence. Competing explanations like dark matter or magnetic fields are still more plausible for now, but the fact that we're even having this conversation shows just how deep the InfraredTeV crisis cuts. It's not just a puzzle about gamma rays. It's a potential window into physics beyond Einstein, beyond the standard model, and into territories we've only dreamed of exploring. So while quantum gravity remains a long shot, it's a reminder that sometimes the biggest answers come from asking the boldest questions. And as our telescopes sharpen and our models improve, we might just find that the universe's smallest secrets are hiding in plain sight, written in the light of its most energetic explosions. Up next, we'll shift gears and look at how our best computer simulations stack up against real-world observations, and where they're falling short in this cosmic detective story. Let's take a step back from the theoretical and look at something more concrete: the clash between what our simulations predict and what we actually see out there in the cosmos. Computer simulations are like cosmic laboratories, letting us test theories about gamma rays without leaving Earth. But here's the catch: when we compare these digital forecasts to real-world observations, things don't always line up. And that mismatch is at the heart of why the InfraredTeV crisis is so perplexing. Picture this: astrophysicists build incredibly detailed simulations that model everything from the birth of gamma rays in extreme environments like supernova or black hole jets to their long journey across the universe. These simulations factor in known physics: how gamma rays interact with interstellar gas, magnetic fields, even the faint glow of starlight. They should, in theory, give us a near-perfect replica of what telescopes like Fermi and HESS detect. But time and again, the real data throws us a curveball. One major discrepancy pops up with blazars, those supercharged galaxies shooting jets of particles straight at us. Simulations predict that the gamma rays from these jets should follow a smooth, predictable pattern as they lose energy traveling through space. Instead, we see wild fluctuations, gamma rays arriving with energies that don't match the models or appearing in bursts that defy expectations. It's like forecasting a gentle rain and getting a hailstorm instead. Then there's the issue of gamma-ray halos. Some simulations suggest that when gamma rays collide with starlight, they should produce a faint, diffuse glow around their sources. Observations sometimes show these halos, but they're often fainter or brighter than they should be. Even stranger, in a few cases, they're completely absent. It's as if the universe forgot to follow the script. Why does this matter? Because simulations are more than just fancy video games for scientists. They're how we stress test our understanding of physics. When reality and simulation disagree, it's a flashing sign that somewhere our assumptions are wrong. Maybe we're missing a key ingredient, like an unknown particle or an overlooked force. Or perhaps the rules themselves need rewriting. Take dark matter, for example. Many simulations include it as an invisible scaffold shaping gamma-ray interactions. But if dark matter behaves differently than we think, say, by interacting with itself or decaying in unexpected ways, our simulations would be off without us realizing it. The same goes for magnetic fields. We know they're out there weaving through space, but if their strength or structure isn't what we've modeled, gamma rays could zig where we predicted they'd zag. The stakes here are high. Every mismatch between simulation and observation forces us to ask, is this a glitch in our models or a glimpse of new physics? The InfraredTeV crisis isn't just about gamma rays acting oddly, it's about whether our virtual universe is missing a chapter. And until we bridge that gap, the mystery deepens. Up next, we'll zero in on one of the biggest troublemakers in this cosmic puzzle, blazars. These energetic powerhouses might hold the key to why our predictions keep falling short, or why we need to rethink everything we thought we knew. Now let's turn our attention to one of the most baffling players in this cosmic drama, blazars. These aren't your average galaxies. Imagine a supermassive black hole, millions of times heavier than our Sun, sucking in matter with such force that it spews out jets of particles moving at nearly the speed of light. Now picture one of those jets aimed directly at Earth. That's a blazar, a cosmic lighthouse flashing its beam straight at us. And when it comes to the InfraredTeV crisis, blazars are at the center of the storm. What makes them so unpredictable? For starters, their gamma-ray emissions don't follow the rules. When astronomers track blazars over time, they expect to see a steady hum of high-energy light, punctuated by occasional flares. Instead, blazars deliver wild, erratic outbursts, gamma rays flaring up or vanishing without warning. Some blazars stay quiet for years, then suddenly blast out enough energy in a single day to outshine entire galaxies. Others flicker like a light bulb with a loose connection, leaving scientists scrambling to explain why. Take the blazar Markarian 421, for example. Back in 2012, telescopes caught it flaring so violently that its gamma-ray output jumped by a factor of 10 in less than an hour. No existing model could account for such a rapid, extreme surge. It's like revving a car engine from 0 to 60 in a blink, except this engine is the size of a solar system. Even stranger, some blazars emit gamma rays at energies so high that they should have been absorbed long before reaching Earth. Yet here they are, defying the odds. The mystery deepens when we look at how blazars interact with infrared light. According to theory, gamma rays from blazars should collide with infrared photons. The faint heat glow from dust and stars and vanish, creating a predictable cutoff in their energy spectrum. But many blazars laugh at this idea. Their gamma rays barrel through infrared light like it isn't even there, showing no sign of the expected absorption. This defiance is a core part of the InfraredTeV crisis. If we can't explain why these gamma rays ignore the rules, we're missing something fundamental about how energy moves through the universe. One leading idea is that blazars might be hiding unseen layers of complexity. Maybe their jets aren't smooth streams but tangled, knotted ropes of magnetic fields and particles, accelerating gamma rays in ways we don't yet understand. Or perhaps the infrared light around blazars isn't uniform clumpy. Patchy clouds could let gamma rays slip through gaps like sunlight through storm clouds. There's even speculation that blazars could be factories for exotic physics, where particles break known laws or decay into unexpected forms. Blazars also throw a wrench into the dark matter debate. Some researchers thought blazar gamma rays might carry hints of dark matter annihilations happening near the black hole. But the signals are so messy and unpredictable that teasing out a dark matter signature feels like searching for a whisper in a hurricane. Until we crack the blazar code, even this tantalizing possibility remains out of reach. What's clear is that blazars aren't just oddballs, they're litmus tests for our understanding of physics. Every erratic flare, every stubborn gamma ray that shouldn't exist, forces us to question whether we've got the full picture. And with new telescopes honing in on these enigmatic objects, the next few years could bring answers or even bigger surprises. Coming up, we'll explore another twist in this cosmic puzzle, how the timing of gamma ray bursts adds yet another layer of confusion to the InfraredTeV crisis. Why do some signals arrive early or late, as if the universe itself can't keep time? Now let's peel back another layer of this cosmic mystery, time itself. If blazars are the unruly actors in this drama, then their timing is the plot twist no one saw coming. Gamma ray bursts and flares don't just defy energy predictions, they mess with our clocks too. Imagine setting a timer for a cake, only for it to bake in half the time or take twice as long with no explanation. That's the kind of chaos we're dealing with in the InfraredTeV crisis. Take one of the most head-scratching observations, gamma rays arriving late. According to Einstein, all light travels at the same speed in a vacuum, the speed of light, obviously. So when a blazar flares, we expect its gamma rays to hit our detectors in sync with lower energy light, like radio or infrared waves, but that's not what happens. Some gamma rays show up fashionably late, as if they took a detour through the universe. Others arrive early, like overeager party guests. This isn't just a small discrepancy, we're talking delays or advances of hours, even days. It's like the universe has a broken metronome. Why does this matter? Because timing is everything in astrophysics. If gamma rays aren't playing by the rules of simultaneity, it challenges our understanding of how these particles are produced and how they travel. One theory suggests that gamma rays might be born in different parts of the blazar's jet than their lower energy siblings. Picture a factory where products roll off the assembly line at random intervals instead of in orderly batches. Maybe the jet's turbulent magnetic fields accelerate particles in bursts, creating staggered emissions. But even this doesn't fully explain the extreme time gaps we observe. Then there's the enigma of orphan flares. These are gamma-ray outbursts with no accompanying flare in other wavelengths, like a firework that explodes silently. Standard models say that when a blazar erupts, it should light up across the electromagnetic spectrum, from radio waves to gamma rays. Orphan flares break that rule, suggesting that gamma rays sometimes operate on their own schedule. Some researchers speculate this could mean hidden processes within the jet, like shock waves or magnetic reconnections, that exclusively pump out high-energy particles. Others wonder if we're missing faint signals in other wavelengths buried in the noise. The plot thickens when we look at repeating patterns or the lack thereof. Some blazars flare quasi-periodically, like a heartbeat, while others are utterly random. For instance, the blazar PKS 2015-541 threw scientists for a loop when it flared roughly every 2 years for a decade, then suddenly stopped. No one knows what flipped the switch. Is something inside the black hole's disk hiccuping at regular intervals? Are interactions with a hidden companion star or black hole stirring the pot? Without a clear mechanism, these patterns are just tantalizing clues. And here's where it ties back to the InfraredTeV crisis. If we can't predict when gamma rays will arrive or how they'll behave, how can we trust our models of their interactions with infrared light? Time variability adds another variable to an already unsolved equation. Maybe the delays are caused by gamma rays bouncing off unseen clouds of infrared photons, creating a cosmic echo effect. Or perhaps the flares themselves are altering their surroundings in real time, like a wildfire changing wind patterns as it burns. The stakes are high because timing anomalies aren't just academic curiosities, they're potential windows into new physics. If gamma rays are somehow interacting with spacetime itself, like quantum foam or extra dimensions, their arrival times could carry hints of these phenomena. It's a long shot, but when the universe keeps handing you puzzles, you can't ignore even the wildest pieces. Up next, we'll see how scientists are tackling this crisis with a powerful new toolkit, multi-messenger astronomy. By combining gamma rays with signals like neutrinos and gravitational waves, we might finally start connecting these dizzying dots. But here's where the story takes a fascinating turn. Scientists aren't just relying on gamma rays to crack this cosmic code anymore, they're turning to a symphony of signals from across the universe. This is the era of multi-messenger astronomy, where gamma rays, neutrinos, gravitational waves, and even cosmic rays come together like pieces of a puzzle. Imagine trying to solve a mystery with only one clue versus having a whole detective's notebook. That's the power of this approach. Take neutrinos, for example. These ghostly particles barely interact with matter, slipping through planets and stars like they're not even there. But when a high-energy neutrino does hit Earth, it often points back to its source like a cosmic breadcrumb. In 2017, the Neutrino Observatory ice cube spotted a neutrino from a blazar called TXS 0506+056. At the same time, Fermi detected a gamma-ray flare from the same object. This wasn't just a coincidence, it was a smoking gun. For the first time, scientists had proof that blazars could accelerate not just gamma rays but neutrinos too. Suddenly, the InfraredTeV Crisis had a new lead. Maybe these anomalies are tied to particles we've barely begun to understand. Then there's gravitational waves, ripples in space-time caused by cataclysmic events like black hole mergers. While we haven't directly linked gravitational waves to blazars yet, future observatories could spot subtle tremors from the supermassive black holes powering these jets. If a gravitational wave signal ever aligns with a gamma-ray flare, it might reveal hidden dynamics inside the blazar's engine, like how the black holes spin or its surrounding disk influences particle acceleration. But multi-messenger astronomy isn't just about adding more data, it's about connecting the dots in ways we couldn't before. Consider cosmic rays, high-energy protons, and atomic nuclei that bombard Earth. Some likely come from blazars, but their charged particles get scrambled by magnetic fields on their way here, making it hard to trace their origins. However, if a cosmic ray arrival lines up with a gamma-ray flare and a neutrino, suddenly we have a trio of messengers painting a clearer picture. It's like triangulating a signal from space. Teams around the world are now racing to coordinate these observations. Projects like the Astrophysical Multi-Messenger Observatory Network, or AMON, act as cosmic switchboards, alerting telescopes globally when multiple detectors pick up signals from the same patch of sky. In 2022, AMON flagged a potential neutrino gamma-ray coincidence from a blazar, triggering rapid follow-up observations across the electromagnetic spectrum. While the results were inconclusive, each attempt sharpens our tools for the next big breakthrough, and the tech is only getting better. Upcoming neutrino detectors like the Cubic Kilometer Neutrino Telescope, or KM3NT, will scan the Mediterranean with thousands of sensors, while gravitational wave facilities like the Laser Interferometer Space Antenna, or LISA, will listen for low-frequency ripples from space. Combine these with gamma-ray telescopes like the Cherenkov Telescope Array, and we're building the ultimate toolkit to dissect the InfraredTeV Crisis. The beauty of multi-messenger astronomy is that it lets us see the universe in layers. Gamma rays might tell us about particle acceleration, neutrinos could reveal the jet's inner workings, and gravitational waves may expose the black hole's dance. Together, they might finally explain why gamma rays don't play by the rules, whether it's hidden matter, unknown physics, or something even stranger. One thing's clear: solving this crisis won't come from a single eureka moment, but from stitching together clues from across the cosmos. And as our detectors grow more sensitive and our collaborations more seamless, the next big revelation could be just one coordinated observation away. Now, let's zoom in on another piece of the puzzle: the cutting-edge technology behind these discoveries, and how their limits might actually be shaping the mystery itself. But even with these incredible tools at our disposal, there's a catch. Our current technology has blind spots, and those gaps might be hiding the very answers we're searching for. Take gamma-ray telescopes, for example. Instruments like Fermi's Large Area Telescope are phenomenal at catching high-energy gamma rays, but they struggle with precision at the highest energies, precisely where the InfraredTeV Crisis gets weird. When gamma rays hit the upper limits of the tera-electronvolt range, our detectors often can't pin down their exact energy or direction with enough accuracy. It's like trying to read a street sign through foggy glasses. You know the sign is there, but the details are blurred. This uncertainty makes it tough to test theories about why these gamma rays don't dim as expected when interacting with infrared light. Then there's the challenge of timing. Gamma-ray flares from blazars can erupt in minutes or even seconds, but not all telescopes can react that quickly. Ground-based Cherenkov telescopes like HESS or MAGIC need clear, moonless nights to operate, and by the time they swing into action, a crucial flare might already be fading. Even when they catch an event, there's often a delay in coordinating with other observatories, neutrino detectors, radio telescopes, or X-ray satellites, meaning we miss the chance to see the full picture in real time. Neutrino detectors face their own hurdles. While IceCube's Antarctic array is a marvel, it's still relatively small in the grand scheme of things. Most neutrinos zip right through it without a trace. To catch more, we need bigger detectors like the upcoming cubic kilometer neutrino telescope, which will turn a chunk of the Mediterranean into a particle trap. But until then, we're working with a sparse dataset, like trying to reconstruct a movie from just a handful of random frames. Gravitational wave astronomy is even younger. Current observatories like LIGO and Virgo are tuned to detect ripples from merging black holes and neutron stars, but the supermassive black holes in blazars, their signals are slower, lower-frequency whispers that slip right past today's detectors. That's why projects like the Laser Interferometer Space Antenna, a future space-based observatory, are so exciting. LISA trio of satellites will listen for these deeper cosmic vibrations, potentially uncovering the hidden rhythms of blazar jets. And let's not forget the infrared itself. The infrared in the InfraredTeV Crisis isn't just a label, it's a critical piece of the puzzle. But our infrared telescopes often lack the sensitivity to map the faint glow of intergalactic dust clouds with enough detail. Without knowing exactly how much infrared light is out there, it's hard to calculate how much gamma-ray dimming should happen. Upcoming missions like the James Webb Space Telescope's successors could fill this gap, giving us sharper infrared eyes on the universe. The good news: the next generation of instruments is already on the drawing board, or in some cases under construction. The Cherenkov Telescope Array, with its hundreds of telescopes spread across Chile and the Canary Islands, will catch gamma rays with 10 times the sensitivity of current arrays. The Square Kilometer Array radio telescope will map cosmic magnetic fields in unprecedented detail, helping us trace how they twist and scatter particles. And then there's the Enhanced X-ray Timing and Polarization mission, which will study the violent environments around black holes with X-ray vision sharper than anything before. These upgrades aren't just incremental, they're transformative. Imagine going from a dial-up internet connection to fiber optic speeds. Suddenly, data that used to take years to collect might stream in within months, revealing patterns we've never seen. And with faster, more sensitive tools, we can test hypotheses in real time, like whether dark matter particles are hiding in gamma-ray shadows, or if blazar jets have secret, turbulent layers we've never detected. But here's the humbling truth: even the best technology can't solve everything alone. Sometimes the universe throws us curves that defy our current frameworks. That's why the InfraredTeV Crisis isn't just a technical challenge. It's a call to rethink how we approach cosmic mysteries. Maybe the answer lies in refining our models, or perhaps it's waiting in a completely new branch of physics we've yet to imagine. What's certain is that every limitation we face today is a roadmap for tomorrow's breakthroughs. And as these new tools come online, they won't just clarify the crisis, they'll redefine how we see the high-energy universe altogether. Now, let's step back and see how this scientific whirlwind is playing out beyond the lab, how the wider world is reacting to a mystery that could rewrite astrophysics. Now, let's turn our attention to how this cosmic puzzle is stirring up excitement far beyond the research labs. The InfraredTeV Crisis isn't just a quiet debate among scientists, it's sparking conversations, controversies, and even a bit of drama in the wider world. When the first puzzling gamma-ray observations made headlines, the astrophysics community reacted with a mix of skepticism and fascination. After all, science thrives on anomalies, those stubborn wrinkles in the data that refuse to fit our neat theories. But this wasn't just a small inconsistency. The InfraredTeV Crisis directly challenged long-held assumptions about how gamma rays interact with the universe. Some researchers initially questioned the data itself, wondering if telescope glitches or calibration errors might be to blame. Others dove headfirst into re-examining decades of gamma-ray models, searching for overlooked details that could explain the mismatch. Conferences quickly became hotbeds for lively discussions. At events like the International Cosmic Ray Conference or the High Energy Astrophysics Division meetings, you'd find researchers huddled in corners, scribbling equations on napkins or debating over coffee. The crisis even split opinions along generational lines. Senior scientists steeped in traditional models often urged caution, emphasizing the need for more data. Meanwhile, younger researchers less tied to old frameworks threw bold new ideas into the ring, from exotic dark matter particles to radical tweaks in quantum gravity. The public's reaction has been equally intriguing. Science communicators and journalists have latched onto the mystery, framing it as a cosmic whodunit. Popular articles describe the missing gamma ray dimming as a celestial magic trick, while documentaries dramatize the hunt for answers with sweeping visuals of swirling galaxies and crackling energy beams. Social media, too, has buzzed with speculation. Amateur astronomers and physics enthusiasts trade theories in online forums, sometimes even spotting patterns professionals missed. But with this spotlight comes a challenge. Sensational headlines occasionally oversimplify the crisis, suggesting it disproves all of modern astrophysics. In reality, scientists see it as a refinement, a sign that our understanding is evolving, not crumbling. To counter misinformation, researchers have taken to YouTube, podcasts, and public lectures, breaking down the nuances in accessible ways. The goal isn't just to inform, but to invite the public into the scientific process, showing how mysteries like this drive progress. Funding agencies have taken notice as well. Grant review panels, once hesitant to back high-risk, high-reward projects, are now more open to proposals targeting the crisis. Philanthropic organizations and even tech billionaires have joined the fray, bankrolling new telescopes or data-crunching initiatives. There's a growing sense that solving this puzzle could unlock breakthroughs far beyond gamma rays, perhaps even touching on dark matter or the nature of space-time itself. Yet amid all this activity, one thing stands out. The crisis has united scientists across borders. Collaborations that once inched forward now move at lightning speed, with researchers sharing data openly and rushing preprint papers online months before formal publication. It's a reminder that while the universe might keep its secrets close, humanity's curiosity is even more relentless. And speaking of curiosity, this isn't just about distant galaxies. The way we grapple with the InfraredTeV crisis could shape the future of astrophysics for decades. Next, let's explore how the scramble for answers is reshaping the economics of science itself. Now, let's pull back the curtain on something just as fascinating as the science itself, the real-world ripple effects of this cosmic mystery. When a puzzle like the InfraredTeV crisis emerges, it doesn't just challenge our theories. It reshapes the very machinery of scientific progress, from funding priorities to the tools we build to chase answers. Take funding, for example. Traditionally, gamma-ray astronomy hasn't always been the flashiest field when it comes to attracting big budgets. Compared to headline-grabbing projects like Mars rovers or gravitational wave detectors, studying high-energy photons from distant galaxies might seem niche. But the crisis changed that overnight. Suddenly, governments and private investors realized that solving this anomaly could crack open bigger questions, like the nature of dark matter or the fabric of spacetime itself. Funding agencies like the National Science Foundation and the European Research Council began fast-tracking grants specifically targeting the crisis. Proposals that might have been deemed too speculative a decade ago are now getting greenlit, with reviewers openly acknowledging that high-risk, high-reward science is exactly what's needed here. Private money has flooded in too. Tech billionaires and philanthropic organizations, always on the lookout for the next big breakthrough, have poured millions into new initiatives. Some fund ultra-sensitive detectors to catch elusive gamma-ray signatures. Others bankroll supercomputing projects to simulate exotic scenarios like dark matter particles colliding in ways we've never seen. There's even a Silicon Valley-backed effort to crowdsource data analysis, inviting amateur scientists worldwide to sift through telescope readings for hidden clues. And then there are the telescopes themselves. Before the crisis, plans for next-generation observatories like the Cherenkov Telescope Array, a global network of gamma-ray detectors, were moving at a cautious, bureaucratic pace. Now, construction timelines have accelerated. Countries that once hesitated to commit resources are suddenly vying to host new telescope sites, eager to be at the forefront of a potential revolution. Even existing facilities like the Fermi-Large Area Telescope or the HESS array in Namibia have seen budget boosts for upgrades, ensuring they can collect crisper, more precise data. But here's the twist. This funding surge isn't just about solving one mystery. It's creating a golden age for gamma-ray astronomy as a whole. Early career researchers who might have avoided the field due to slim job prospects are now diving in, lured by the excitement and the sudden abundance of opportunities. Universities are launching new courses on high-energy astrophysics, and collaborations between institutions have multiplied. The crisis has effectively turned a specialized corner of science into a thriving global enterprise. Of course, with more money comes more scrutiny. Critics argue that the frenzy around the InfraredTeV crisis risks diverting funds from other critical areas, like climate science or medical research. Proponents counter that unlocking cosmic mysteries often leads to unexpected technological spin-offs. Think how satellite tech revolutionized communications or how particle physics gave us the World Wide Web. Either way, one thing's clear: the economic stakes of this scientific saga are as sky-high as the gamma rays themselves. And speaking of stakes, this isn't just about dollars and telescopes. The way we navigate this funding boom could set a precedent for how humanity tackles future cosmic riddles. Next, we'll see how scientists across the globe are banding together in ways no one predicted. Now, let's turn our attention to one of the most inspiring aspects of the InfraredTeV crisis, the way it's uniting scientists across borders like never before. When a cosmic puzzle this big emerges, no single country or institution can crack it alone. That's why researchers from every corner of the globe are joining forces, pooling their expertise, and breaking down traditional barriers in the name of discovery. Take the Cherenkov Telescope Array, for example. This ambitious project isn't just a collaboration between a handful of labs. It's a worldwide effort involving over 1,500 scientists from 31 countries. From the high deserts of Chile to the volcanic peaks of the Canary Islands, teams are working in lockstep to build the most sensitive gamma-ray observatory ever conceived. What's remarkable is how quickly rival agencies have set aside competition for cooperation. NASA engineers are sharing designs with their European and Japanese counterparts, while universities in South Africa and Australia are contributing cutting-edge software to process the flood of data. It's a testament to how urgency can redefine partnerships. Then there's the Fermi-LAT Consortium, a group that reads like a scientific United Nations. When the telescope began spotting anomalies in gamma-ray bursts, researchers from Italy to India scrambled to reinterpret the data together. Weekly virtual meetings now stretch across time zones, with theorists in Brazil debating models alongside observers in Germany. Even historically isolated space programs like China's National Space Science Center have opened their archives, allowing global teams to cross-check findings against previously restricted datasets. This level of transparency would have been unthinkable a decade ago, but the crisis has made it necessary. But it's not just about big institutions. Grassroots collaborations are flourishing too. Platforms like Zooniverse have enabled amateur astronomers and citizen scientists to classify gamma-ray events alongside professionals. A high school teacher in Norway recently helped identify a blazar flare that had been missed by automated systems, proving that fresh eyes, no matter where they are, can spot what algorithms overlook. Meanwhile, open-source initiatives led by universities in Canada and the Netherlands have created shared code repositories where anyone can test new analysis techniques. The result, a democratization of science that's accelerating progress. Of course, collaboration isn't without its challenges. Coordinating between cultures, languages, and academic traditions requires patience. A team in France might prioritize elegant theoretical frameworks, while their partners in the United States push for rapid observational campaigns. But these differences are becoming strengths rather than obstacles. The diversity of approaches has led to creative solutions, like hybrid models that blend real-time data with long-term simulations. What's truly exciting is how these partnerships are training the next generation of scientists. PhD students in Mexico are co-authoring papers with senior researchers in Japan, while postdocs in Kenya are leading telescope calibration efforts with support from Swedish mentors. This crisis isn't just producing new knowledge, it's forging a global network of thinkers who'll tackle future mysteries with built-in connections across continents. And that's the bigger picture here. The InfraredTeV Crisis has shown that when humanity faces a cosmic question mark, borders blur and curiosity becomes the common language. Up next, we'll explore how this shift is reshaping classrooms and inspiring young minds to aim for the stars literally. Now, let's step into the classroom and see how this cosmic mystery is shaping the minds of future scientists. The InfraredTeV Crisis isn't just a topic for research papers, it's rewriting textbooks and transforming how astrophysics is taught. Universities worldwide are using this puzzle as a living case study, showing students that even our most trusted models of the universe are open to question. At MIT and Caltech, graduate seminars now dedicate entire modules to the crisis, challenging students to dissect the discrepancies between theory and observation. Professors aren't handing down answers, they're guiding students through the same uncertainties professionals face. One MIT student recently told me how her class spent weeks debating whether the anomalies stem from dark matter or flawed detector calibrations, mirroring real scientific discourse. It's a far cry from memorizing equations, and it's preparing a generation comfortable with ambiguity. Meanwhile, undergraduate labs are getting creative. Instead of canned experiments with predictable outcomes, schools like Stanford and University College London have designed courses where students analyze raw Fermi-LAT data, hunting for their own patterns in the noise. A group at UCL made headlines last year when their classroom project uncovered a subtle timing glitch in gamma ray burst records, a glitch that later helped explain some of the erratic readings. These hands-on experiences prove that even beginners can contribute to frontier science. The crisis is also democratizing access to cutting-edge tools. Platforms like Google Colab now host Jupyter notebooks with simplified versions of professional analysis pipelines, allowing students from Lagos to Lima to work with the same datasets as tenured professors. I spoke to a lecturer in Kenya who uses these resources to teach coding and astrophysics simultaneously, showing students how to write Python scripts that filter TV energy events from telescope noise. For many, it's their first taste of big data science, but perhaps the most profound shift is in mentorship. Senior researchers grappling with the crisis are bringing students into the fray earlier than ever. At Princeton, a team investigating quantum gravity's role in the anomalies includes 2 sophomores co-authoring papers. Their advisor told me, "If we're questioning century-old assumptions, why shouldn't fresh perspectives be part of the conversation?" This apprenticeship model is producing graduates who enter the field already versed in its biggest open questions. The ripple effects reach beyond physics departments. Philosophy courses now cite the crisis when discussing scientific revolutions, while engineering schools use gamma-ray detector designs as capstone projects. Even high schools are adapting. A teacher in New Zealand developed a board game where students play as competing theories trying to explain the anomalies, blending strategy with cosmic physics. What's emerging is a new educational ethos that prizes curiosity over certainty. As one Oxford professor put it, "We're not just teaching astrophysics anymore, we're teaching how science evolves when it hits a wall." And for students, that's exhilarating. Applications to astrophysics programs have surged, with personal essays increasingly citing the crisis as motivation. These aren't just future researchers, they're potential solvers of one of space's greatest riddles. As we look ahead, the classroom innovations sparked by this mystery may endure long after the crisis itself is resolved. Because when students learn that even experts don't have all the answers, they're not just studying science, they're living it. But beyond the equations and telescopes, this crisis invites us to ask deeper questions, the kind that tangle with the very nature of science itself. What does it mean when our most trusted tools for understanding the cosmos suddenly fall short? The InfraredTeV crisis isn't just about gamma rays. It's a humbling reminder that the universe still holds cards we haven't even glimpsed. Consider how this challenges our assumptions about progress. For decades, astrophysics marched forward with a quiet confidence, stitching together a working model of everything from black holes to the Big Bang. Now, with gamma rays behaving like cosmic loose threads, we're forced to reckon with the possibility that some of our foundational ideas might be incomplete or even wrong. It's uncomfortable, sure, but also thrilling because this is how real breakthroughs happen. History shows us that every major leap in science, from relativity to quantum mechanics, began with an anomaly someone refused to ignore. Then there's the question of scale. The fact that we're stumbling over phenomena occurring at both infrared and tera-electronvolt energies ranges separated by a factor of 1 trillion, hints that we might be missing connections between the very small and the unimaginably vast. Could this crisis be a signpost pointing toward some deeper unity in physics, a bridge between quantum weirdness and cosmic structure? Some theorists whisper about parallels to past revolutions, like when Maxwell linked electricity and magnetism in the 19th century. But this time, the stakes feel higher, the unknowns vaster. Science thrives on certainty, but what happens when certainty crumbles? The crisis has sparked fierce debates about how much trust we should place in our models. On one side, traditionalists argue that anomalies like these will eventually fold neatly into existing theories with minor tweaks. Others, though, see this as a crack in the foundation evidence that we need entirely new frameworks. It's a tension as old as Galileo, playing out now in conference halls and arXiv preprints, and it forces us to confront an uncomfortable truth. Our maps of reality are always provisional, subject to revision by the next unexpected observation. Perhaps most intriguing is what the crisis says about human curiosity. In an era where some claim science has solved the big questions, here's a glaring exception, one that's mobilized labs across the planet. There's something poetic about astronomers peering at ancient light from distant galaxies, only to find fresh mysteries in their own data. It suggests that wonder isn't just for textbooks or planetarium shows, it's woven into the fabric of professional discovery. And let's not forget the collaborative spirit this has unleashed. The crisis can't be solved by any one team or telescope. It demands pooled data, shared code, and interdisciplinary thinking. That shift from competition to collective problem solving might be its most enduring legacy. Because if the universe is more complex than we imagined, maybe our approach to understanding it should be too. So as we watch this story unfold, remember, the InfraredTeV Crisis isn't just a puzzle for astrophysicists. It's a live demonstration of science as a process messy, exhilarating, and gloriously unfinished. And that, in the end, might be the most important lesson of all. Now, let's turn our gaze toward the horizon where the next generation of telescopes and missions promises to shed light on this cosmic mystery. The Cherenkov Telescope Array, or CTA, stands at the forefront of this effort. Unlike traditional telescopes that capture visible light, the CTA is designed to detect the faint, blue flashes of Cherenkov radiation produced when gamma rays collide with Earth's atmosphere. This next-level observatory, with its network of over 100 telescopes spread across the Canary Islands and Chile, will offer unprecedented sensitivity to the highest energy gamma rays. Imagine it as a cosmic detective picking up whispers from the universe that current instruments simply miss. But the CTA isn't alone in this hunt. The upcoming Advanced Gamma Ray Imaging System, or AGIS, aims to complement these efforts with even sharper resolution. Then there's the eagerly anticipated James Webb Space Telescope's infrared capabilities, which could reveal how lower energy photons interact with the same mysterious processes troubling the high-energy gamma ray world. By bridging these energy gaps, we might finally spot the hidden patterns connecting them. Meanwhile, space-based missions like the European Space Agency's Theseus satellite are set to launch in the coming years, focusing on transient events, sudden, fleeting bursts of gamma rays that could hold clues to the crisis. These missions represent more than just technological marvels. They're bets placed by the scientific community, wagers that somewhere in this deluge of new data, the universe will slip up and reveal its secrets. What makes this moment especially exciting is the potential for synergy. For the first time, instruments capable of observing across the entire electromagnetic spectrum, from radio waves to tera-electronvolt gamma rays, will operate simultaneously. This multi-wavelength approach is like assembling a jigsaw puzzle where each telescope contributes a missing piece. For instance, while the CTA pinpoints high-energy anomalies, radio telescopes like the Square Kilometre Array could trace the magnetic fields that might be bending or distorting gamma rays in unexpected ways. And let's not overlook the role of computational advancements. Machine learning algorithms are now being trained to sift through petabytes of data, searching for subtle correlations that human eyes might miss. These tools could uncover hidden links between seemingly unrelated phenomena, perhaps showing how a flicker of infrared light from a distant galaxy aligns with a gamma ray flare detected years later. Of course, every new tool brings new questions. Will these observations confirm existing theories, or will they deepen the crisis by revealing even more perplexing behavior? Some researchers caution that we might be on the verge of a data deluge that overwhelms rather than clarifies. Yet history suggests otherwise. It's often in the flood of unexpected findings that breakthroughs emerge. As these missions come online, they'll do more than test hypotheses. They'll redefine how we explore the unknown. The InfraredTeV Crisis has already shown us that the universe is far stranger than we imagined. Now, armed with these cutting-edge tools, we're not just waiting for answers, we're building the means to demand them. The next decade promises to be a golden age for gamma-ray astronomy, one where collaboration between humans and machines, ground and space, might finally untangle this cosmic knot. And as the data rolls in, remember, every flicker of light captured by these telescopes isn't just a photon, it's a potential clue in the greatest detective story of all time. Now, let's peer into the future and imagine how this cosmic puzzle might finally be solved. The InfraredTeV Crisis has already shaken our understanding of gamma rays, but the next decade could bring breakthroughs that rewrite the textbooks. Here's where the story gets thrilling, because science is on the verge of some truly game-changing discoveries. One of the most promising avenues involves dark matter. We've long suspected that this invisible substance makes up most of the universe's mass, but it's never been directly detected. What if the anomalous gamma rays are actually signals of dark matter particles colliding and annihilating? Experiments like the Cherenkov Telescope Array could spot telltale patterns in gamma ray emissions, clumps of high-energy light coming from regions where dark matter is thought to cluster, like the centers of galaxies. If these patterns match predictions, it would be a monumental discovery, finally revealing the nature of this elusive cosmic ingredient. Then there's the possibility of entirely new physics. The Standard Model, our current rulebook for how particles and forces interact, might be incomplete. Some theorists suggest that gamma rays could be interacting with unknown particles or forces in ways we haven't yet imagined. For instance, quantum gravity, a theory that merges quantum mechanics with Einstein's general relativity, could leave faint fingerprints in gamma-ray data. While this idea remains speculative, next-generation telescopes might catch glimpses of these effects, especially if gamma rays behave oddly when traveling across vast cosmic distances. Another exciting angle revolves around cosmic accelerators, natural machines in space that boost particles to unbelievable energies. We know supermassive black holes and supernova remnants can act like cosmic particle colliders, but what if there's something even more powerful out there? Future observations might uncover exotic objects like magnetars with ultra-strong magnetic fields or merging neutron stars that pump out gamma rays in ways we've never seen. The key could lie in timing. If gamma-ray flares coincide with other cosmic events like gravitational waves or neutrino bursts, it would point directly to their source. Technology itself might hold the answer. Machine learning is already transforming how we analyze data, but future algorithms could spot connections no human would ever notice. Imagine an AI detecting a subtle link between gamma-ray flares and infrared emissions from distant dust clouds, a clue that current models missed entirely. Or consider advancements in detector sensitivity. If new instruments can pick up fainter or faster gamma-ray signals, we might catch cosmic processes in action, revealing the mechanics behind the anomalies. Of course, breakthroughs often come from the unexpected. History shows that the biggest discoveries, like the cosmic microwave background or gravitational waves, emerged from surprises, not just targeted searches. The same could happen here. Maybe a telescope designed for one purpose will stumble upon a gamma-ray signal so bizarre it forces us to rethink everything. Or perhaps a citizen scientist sifting through public data will spot the crucial anomaly that cracks the case wide open. The beauty of this moment is that we're not just waiting for answers, we're actively building the tools to uncover them. Every new telescope, algorithm, and theory brings us closer to solving the infrared TV crisis. And when the solution arrives, it won't just explain gamma rays, it could reveal entirely new chapters in our understanding of the universe. So keep watching the skies, because the next big discovery might be just around the corner. Now, let's take a step back and consider a question that often goes unasked in the excitement of scientific discovery. When humanity faces so many urgent challenges here on Earth, how do we justify pouring resources into solving cosmic mysteries like the infrared TV crisis? It's a dilemma that strikes at the heart of how we prioritize knowledge itself. On one hand, some argue that fundamental research studying phenomena with no immediate practical application is a luxury we can't afford when climate change, poverty, and disease demand so much attention. Telescope arrays and space missions cost billions, and that money could fund healthcare, education, or renewable energy projects. Why chase gamma rays from distant galaxies when children lack clean water or vaccines? These critics point out that even if we solve the infrared TV crisis, the answer may not feed the hungry or cool the planet. But here's the counterpoint: history shows that abstract research often yields unexpected, life-changing benefits. Take quantum mechanics. A century ago, scientists probing the bizarre behavior of atoms had no idea their work would lead to computers, MRI scanners, and solar panels. Similarly, studying gamma rays could unveil new physics with revolutionary applications, perhaps novel energy sources, medical imaging techniques, or materials science breakthroughs. The catch: we can't predict which useless discovery will transform society next. Then there's the deeper ethical dimension. Curiosity is part of what makes us human. Civilizations are remembered not just for solving practical problems, but for pushing the boundaries of understanding. When we stop asking why about the universe, we risk losing something vital: the drive to explore, innovate, and see beyond immediate needs. Funding fundamental science is, in a way, an investment in humanity's future intellect and spirit. Balance is key. The real ethical question isn't whether to fund gamma-ray research, but how to distribute resources wisely. Could we trim bloated military budgets instead of science grants? Could wealthy nations invest more in both particle physics and poverty alleviation? The infrared TV crisis reminds us that knowledge isn't a zero-sum game. With thoughtful choices, we can reach for the stars while keeping our feet firmly on the ground. Ultimately, this isn't just about gamma rays. It's about what kind of civilization we want to be. One that only solves today's problems, or one that also plants seeds for a wiser, more enlightened tomorrow. The answer, much like the gamma rays themselves, may not be what we expect. Now, shifting our gaze from the ethics of funding to the broader cultural impact, let's explore how the infrared TV crisis has woven its way into pop culture. After all, when science throws us a curveball as dramatic as gamma rays defying expectations, it's only a matter of time before filmmakers, authors, and artists seize the mystery for their own creative ends. Take Hollywood's love affair with cosmic puzzles. While the infrared TV crisis hasn't yet spawned a blockbuster franchise, its themes echo in sci-fi hits like Interstellar and Arrival, where scientific enigmas drive the plot. These stories thrive on the tension between what we know and what we can't explain, precisely the allure of our gamma-ray conundrum. In lesser-known indie films and TV series like Devs or The OA, you'll spot subtle nods to astrophysical anomalies that mirror real-world crises, using them as metaphors for humanity's thirst for answers. Literature, though, has been quicker to dive in. Science fiction novels, from hard sci-fi by authors like Alastair Reynolds to more speculative works by Kim Stanley Robinson, often toy with the idea of physics behaving unpredictably. Some explicitly reference the infrared TV crisis as a springboard for tales about alternate dimensions, alien technologies, or cosmic forces beyond our comprehension. Even comic books have flirted with the idea. Marvel's Ultimate series, for example, pits heroes against universe-breaking physics glitches that feel eerily familiar to real astrophysicists. But here's where it gets fascinating. These portrayals shape how the public perceives real science. When a thriller like Event Horizon equates gamma-ray anomalies with supernatural horror, or a novel like The Three-Body Problem ties them to existential threats, audiences walk away with heightened fascination or fear. This creates a double-edged sword. On one hand, pop culture sparks interest in astrophysics, drawing new minds to the field. On the other, it risks oversimplifying or sensationalizing the crisis, leaving viewers with the impression that gamma rays are cosmic boogeymen rather than natural, if puzzling, phenomena. Social media amplifies this effect. Viral tweets about mystery rays from deep space or TikTok explainers, some accurate, some wildly speculative, fuel public debate. Memes joking about physics being broken make the crisis feel relatable, but they can also trivialize the painstaking work of scientists. The challenge: harnessing this cultural buzz to educate without diluting the science. Perhaps the most telling impact, though, is on younger generations. When kids see the InfraredTeV Crisis referenced in shows like Doctor Who or video games like Mass Effect, it plants seeds of curiosity. Suddenly, telescopes aren't just tools, they're portals to unraveling the universe's greatest secrets. This cultural crossover reminds us that science doesn't exist in a vacuum. It's a living, breathing part of our collective imagination, inspiring the next wave of researchers who might one day solve the crisis or encounter the next great cosmic riddle. So, while gamma rays might not dominate box offices yet, their cultural footprint is undeniable. From page to screen, these stories reflect our timeless obsession with the unknown, proving that the InfraredTeV Crisis isn't just a scientific challenge, it's a mirror held up to humanity's endless wonder. Now, let's turn the spotlight over to you, because science isn't just a one-way conversation. The InfraredTeV Crisis is one of those rare puzzles where even the experts are scratching their heads, which means your theories might be as valuable as anyone's. Imagine this: somewhere in the comments section right now, there could be an idea that nudges us closer to solving this cosmic riddle. Maybe you've wondered if dark matter particles are interacting in ways we haven't modeled yet, or if there's a hidden layer to quantum gravity that only reveals itself in these extreme energies. Or perhaps you've got a wild, out-of-the-box thought like gamma rays being signatures of advanced alien tech. However you slice it, this is your chance to join the debate. Think about the times in history when breakthroughs came from unexpected places. Kepler's laws of planetary motion, inspired by his obsession with musical harmonies. The structure of benzene, Kekulé dreamed it up after visualizing a snake biting its own tail. Sometimes the missing piece isn't in a lab, it's in a fresh perspective. So don't hold back, drop your questions below. What part of the InfraredTeV Crisis fascinates you the most? Do you think we're missing a fundamental force, or could it be something simpler, like a flaw in our detectors? And if you're feeling hesitant because you're not an astrophysicist, remember, this mystery belongs to everyone. Some of the best discussions happen when people from different backgrounds collide. A gamer might spot a pattern in the data that mirrors a puzzle they've solved virtually. An artist might visualize the problem in a way that sparks a new analogy. Science thrives when it's a team sport, and your voice matters here. To keep the conversation rolling, I'll jump into the comments too. Let's tackle the big questions together. Why do gamma rays at TV energies seem to vanish when infrared light is present? Could this be a clue about the fabric of space-time itself? Or is it a cosmic illusion, like seeing a mirage in the desert? Whatever your take, share it, because the next aha moment might start with you. And hey, if you've got a friend who loves a good mystery, tag them below. The more brains we have on this, the better. After all, the universe isn't just giving us a riddle, it's inviting us all to play. So, what's your theory? Let's hear it. After diving deep into the mysteries of gamma rays and their puzzling behavior, let's take a step back and piece together what we've uncovered. The InfraredTeV Crisis isn't just another cosmic oddity. It's a glaring reminder that the universe still holds secrets even our most advanced theories can't yet explain. From the way gamma rays unexpectedly dim in the presence of infrared light to the baffling contradictions spotted by telescopes like Fermi-LAT, this crisis has shaken the foundations of astrophysics. But here's the thrilling part. Every unanswered question is an invitation to explore further, to rethink what we know, and to push the boundaries of human understanding. Think about what this means for science as a whole. The InfraredTeV Crisis isn't just a problem for astrophysicists, it's a challenge that stretches across disciplines, from quantum mechanics to cosmology. It forces us to confront the gaps in our models, whether that's the elusive nature of dark matter, the quirks of intergalactic magnetic fields, or even the possibility of physics beyond the standard model. And while that might sound daunting, it's also incredibly exciting. After all, some of history's greatest breakthroughs came from moments just like this, when the universe refused to follow the rules we'd written for it. So where does that leave us? For starters, it means the next decade of astronomy could be revolutionary. Upcoming projects like the Cherenkov Telescope Array promise to shed light on these anomalies, potentially unlocking answers or revealing even deeper mysteries. But more than that, the InfraredTeV Crisis is a testament to the spirit of scientific inquiry. It's a reminder that curiosity doesn't end with what we know, it thrives on what we don't. Whether you're a seasoned researcher or someone who simply gazes at the night sky in wonder, this puzzle belongs to all of us. As we wrap up, here's the big takeaway. Science isn't about having all the answers. It's about asking the right questions, staying open to surprises, and embracing the fact that the universe is always one step ahead. The InfraredTeV Crisis isn't a dead end, it's a doorway. And who knows, the solution might come from a telescope yet to be built, a theory yet to be written, or even an idea yet to be shared in the comments below. If this journey through the mysteries of gamma rays has sparked your curiosity, hit that like button. It helps others discover these cosmic conversations. Don't forget to subscribe so you won't miss the next breakthrough in this unfolding story. And as always, keep looking up. The universe has a way of surprising us when we least expect it.